Okay, we are recording, we are live, audio and video is up. I hope everybody had a great weekend. We are in lecture 21, so I think it's fair to say that we're pretty much right at the middle of the semester, and we are rocking and rolling in the world of structural analysis. We're going to continue our discussion on deflections, and today and really for this whole week, and probably a bit into next, we're going to be focusing on flexural deflections, or shorthand, we're talking about deflections of beams. Now, we're going to be using virtual work, the same principle, the same method that we did with trusses. You know, we have our original structure, or what we'll call the real structure, with the original loads present, and then we'll have a virtual structure, which is all that we take all the loads off and we only put a single unit load where we want to find the deflection in the direction that we assume that deflection is occurring. And then we apply the same principles. But the difference between what happens with a truss and what happens with a beam is that the loads are variable. And by loads, because we're talking about beams, we mean moments. So the moments are variable. With a truss member, the trusses were constant, or the forces were constant. And so how we deal with variable loads versus a constant load is a bit different, okay? And so I kind of want to set the stage for that by going back to truss members, and then I want to sort of take a second and ask, well, what if the loads were variable for a truss, and show you what happens differently, and then I think it'll set the stage for beams quite nicely. So let's recap what we're talking about with virtual work for truss displacements. So if we want to compute the displacement of a truss joint, and I'm putting here using typical US customary units, we basically are summing up the U2 for every member, because remember we looked at the external work done and the internal stored energy, and we took that U2 component of the stored energy and set that equal to P delta, and because P was 1, that was it. So we're just summing up the energy for all of the members. And how do we compute that energy? Well, we need the member length, each member length, which needs to be in inches because of units. We need the modulus of elasticity for each member, and we need the cross-sectional area for each member. And then we need two more quantities. We need the internal member forces from real loads, from the original loads on the truss, and then we need the internal member forces from the virtual loads. I probably have like maybe a slight typo here. It probably should say either a comma there, or internal member forces from real loads, internal member forces from virtual loads. I'll fix that later. And again, for your virtual loads, we place a single load on the truss at the joint of interest. Its magnitude is 1 and in the assumed direction of displacement. Now, here's the thing. This formulation assumes that the forces are constant along the member length, which for a truss is absolutely correct. I mean, once you determine that a truss member experiences 25 kips in compression, say, it's 25 kips in compression along the entire member. It doesn't change from one end of the member to the other. So this formulation is fine. But I want to show you real quick what happens if that doesn't work. What if the loads are variable? And so let's take a truss member and let's just sort of walk through this. And again, like I said, we might be delving into calculus land a little bit, okay? So here's a truss member, and this truss member has some length L, and it's made out of some material with a Young's modulus of E, and it's about yay big around with some cross-sectional area A, okay? And we yank on it, okay? Now, when the load is constant, okay, how did we determine the deflection? We determined the deflection by saying FL over EA. And that's how we determined the deflection if the load was constant. But here we're going to say the load isn't constant. We're going to say the load changes across the member. In other words, I might have a different load here than I do here, than I do here, or do I here. So because the load is different, we're going to have to handle this a bit differently. And so the way that we're going to do this is we're going to look at a tiny little sliver, a differential element dx, and see what's going on here. So let's take a look at this little differential element. And so I've got some little tiny sliver dx, and we're going to yank on it, and it's going to stretch some amount d delta. And so how do I compute this d delta? Well, I basically use the same philosophy. I say d delta is the internal force, which in this case is a function, right? It's f of x, right? Times the length, which the length isn't L, I'm talking about this little tiny element. So the length is dx, okay? So force times length divided by EA, okay? And so it's basically the same formula, only instead of the length, I'm using the length of this tiny element, and instead of just a constant force, it's a variable. It's a force as a function of x, okay? And so here's my displacement. If I want to determine the energy, remember that U quantity, we used U2. How do I determine U2? Well, if you remember down here, U2 was the force times the displacement of the whole member, so just force times displacement here. And instead, what I'm going to do is I'm going to take, that virtual force, which itself might be a function, who knows, that might be a function of x, and I'm going to multiply it by d delta, and then I'm just going to integrate, okay? Because, and I mean, don't let integrals scare you, because all an integral is taking, the response on a little tiny element and just summing it up. So if I expand this a bit, I'm going to get U2 is what? Okay, so we're going to have an integral. We're going to have fx. I'm going to have d delta, which is this term here. My limits for my integration are just x equals 0 to x equals L. And that's it, okay? So when I throw this formula out here, I don't want you to think that I'm just, making this up. Like, where did he get this? I'm just taking the same philosophy and just writing it in this format. Now, the real test is, well, what happens when this and this are constants? Do we still get to this same answer here? And it's actually pretty easy to see. So imagine if your little f and your big F are constants. Well, let's go back to Calc 1, right? If I have a constant in an integral, I can factor the whole thing out. So imagine what would happen if I factored all of these constants out. I'd have a little f, a big F, an E, and an A, and then what would be left inside the integral? It would just be dx, evaluated from 0 to L. And so the question is, what is the integral of dx from 0 to L? Well, the integral of dx from 0 to L is x, right? The integral of dx is x, and so we plug in the top number minus plug in the bottom number, and so L minus 0 is L, and we get the same thing that we had before. So the principle works, just this formula might look a little more complicated than this, but really this is a bit more general than this. This formula works all the time, but if your loads are constant, this formula reduces to that. All right, let me pull that up on the slide so that you can kind of see, because I wanted to walk through that with you because I knew that there was a lot of math there. So what I have here on the slide is basically what I have here on the board, just sort of written out a little more, instead of what I did on the board, feeding it to you a little bit at a time, this is just all of it all at once. So up here on the top right, this is the formula that we're using, which again, we're basically just summing up the U2 quantity for each member, but that assumes constant displacements. What I'm doing down here is, well, what happens when we have a variable force? And so I'm just writing it in terms of f of x, and then ultimately plugging and chugging to get this term here. Okay, before I move on, I want to see if there's any questions on this. The last thing I want to do is rush through this. I want you to understand what we're doing and why we're doing it. Everybody good with this so far? I'll take a sec on this. I just want to make sure the idea sticks. I'm not going to make you do this for a Truss member. I just want the concept to make sense. I know it's probably been a while since you've done this mechanics of materials stuff. Let me erase this board because I'll probably use some of this. All right. Okay, I just want to plant that in your head. Let's jump right into the world of beam deflection. Now, what I'm going to do for deflections in beams is this. Ultimately, we're going to arrive at a straightforward process for virtual work. So to give you an idea, if we wanted to compute axial displacement, I might say the integrals of little f, big F over EA. And that might be a straightforward, one-size-fits-all formula for axial displacements. If I'm talking about flexural displacements, I'm going to have a very, very similar formula. Instead of little f's and big F's, it's going to be little m's and big M's for bending moments. And then instead of EA on the bottom, what I'm going to have is EI. Okay? And so ultimately, when it's all said and done, this is what I'm going to try and get towards is this expression here. But I want to take my time and make sure that everybody understands how we go from here to here. Like, how does this term magically become I? Why are we using bending moments and what have you? And so I want to take my time with that. And in order to do that, the first thing that I've got to do is I have to go, to square one with beam deflections, and I have to derive our basic relationship, our basic differential equation that we use to define how beam deflections work. Now, before anybody freaks out, we're not going to be solving differential equations in here. So we're not doing that. So I don't want you to think, oh God, not Math 335. We're not doing that. We're just trying to describe that process. But I want to set the stage for what we're going to do. Okay, so let's get into this derivation, and I want to go through this derivation, but I don't want to just start throwing a bunch of math terms at you. So I want to take it slowly and make sure that you follow along what I'm doing and why I'm doing it. So we're talking square one. Okay, so I've got some math preliminaries I want to walk through with you, and the first one is the area under a curve. So this is a quick review of what I'm calling section properties. So if I have some area or a shape, or maybe what I'll call a section, what are some properties of that section that are relevant to us as engineers? So let's consider a function f of x that's bounded by the x-axis between a and b. And so we can define the area under that curve as the integral of that function evaluated from x equals a to x equals b. That is Calc 1 fundamentally in a nutshell. Okay. Now, one of the things I'm doing here is I'm going to write this sort of in a shorthand fashion in some of these slides, and I'm going to use this notation here. So it's just the integral over some region of dA. And so the idea behind that is, let me see if I can use my mouse, is that, remember, when you're doing integrals, what you're doing is you're summing up those little tiny rectangles across the region. And so what I'm saying is that each of those rectangles are dx wide and f of x tall. And so the area of each of those little rectangles I'm calling dA, so just f of x dx. It's just sort of a shorthand way of writing the area. Okay. Now hopefully that should be pretty easy. That by now that area under a curve is pretty straightforward. What I want to do now is I want to define what are called moments of this area. So if the integral of dA gives you the area, what I can do is take the integral of x dA, or the integral of x squared dA, or the integral of x cubed dA, or x to the fourth dA, or I can take the integral of y times dA, or the integral of y squared times dA. And what I'm doing there is I'm taking what are called moments of an area. And so you can think about this from a statics or structures perspective. How do we define a moment? It's a force times a distance, or a moment arm. It's the same idea here. So like the first moment of area would be the integral of x dA, or the integral of y dA. And the second moment of area would be something like the integral of x squared dA, or the integral of y squared dA. Now, first off, we could go on. We could define, third moments of area, fourth moments of area, 87th moments of area. But what we find in most engineering practice is that really the first two are the only ones that are really useful. For example, the first moment of area is how we determine the centroid of a given shape. So if you take the integral of x dA and you divide it by the integral of dA, that's like saying the sum of ax divided by the sum of a, and you're determining the centroid, right? That's how you determine the centroid of a given shape. Okay. Similarly, so the first moment of area is useful in an engineering perspective to determine the centroid. The second moment of area is useful because of what we're talking about today. The second moment of area has a very special name in engineering practice, and it's called the area moment of inertia, or sometimes it's just called the moment of inertia because it's so common. And the moment of inertia is relevant because it shows up in the derivation for the deflection due to a beam and for the stresses that you get in an element due to moment. That's where this term comes from. One final point I'll mention, it doesn't really matter for our derivation, but it might look like that there's a typo here because I've got qx is the integral of y dA. So like, why are the symbols flipped? The reason why they're flipped is because, if you're if you have a point, like an XY point on a coordinate system. So let's say you have a coordinate system and you have a point right there. God, that is a horrible coordinate system. But you might ask yourself, how far is that point from the x-axis? Like, how would you define how far that point is from the x-axis? And the answer would be y. Okay, so that's why they're flipped. Okay. Last thing I want to show you from a math preliminary standpoint is I want to talk about derivatives. Okay, so if I have a given function f of x, we can compute the following. And so, you all should remember from Calculus 1 that if I have a function, I can determine the slope of that function using the first derivative. And I can determine the concavity of a function by using the second derivative. Right? That should be pretty clear from calculus. Now, one thing I bet that you probably don't remember, and that's okay because it's a little bit of an esoteric formula, is how to determine the curvature of a function. So the slope is found by the derivative, the concavity is found by the second derivative. What about the curvature of a function? The curvature of a function is defined by the quantity that you see down here. If any of you still have your Calc 1 textbook, open it up and go to the index and find curvature of a function, turn to that page, you'll find this formula. So when I pull this out later, I just want you to, that's basically where it came from. Now, another thing that you'll find in math textbooks is that the curvature of a function is related to its radius of curvature by just the reciprocal. And so what do I mean by curvature? This is what I mean. So if I have a beam, let's say here's the beam, and the beam undergoes bending. What we're going to do from a derivation perspective is we're going to assume that this is kind of like the arc of a circle, okay? And so we're going to try and determine its curvature. And so the radius of curvature, think if this is kind of like the arc of a circle, where would the center of that arc be? I don't know, looking at the camera, maybe like somewhere like way up here. And so the radius of curvature would be however far it is from that center to the curves. That's what I mean by radius of curvature. All right. Okay, before we move on, everybody good with preliminaries? Everybody good so far? Okay. All right. So let's talk about our beam deflection. So the mechanics for beams and frames are a little different. We're going to make some similar assumptions. So we're going to assume that the behavior is linear and elastic, just like we had before. We're going to assume that the deflections are small. And we might talk a little bit more about that later, but small deflection theory just means that we don't have to go back and refigure out equilibrium for the structure after it's deformed. That the displacements are so small that it's like your reactions don't change, your shear moment diagrams don't change. It doesn't really matter too much for what we're talking about today, but I just want to lay that out there so that we're clear on that. Okay, so when you have a beam that's deformed, it looks kind of something like this. And so what I'm going to do is I'm going to isolate a little tiny portion of that and see if I can determine some things about its stresses or strains. Now what I'm going to do is I'm going to take that tiny segment and I'm going to kind of blow it up. When I blow it up, it's going to look like this. Now I want to be clear that this beam is undergoing a very exaggerated deformation. Like what you see here on the slide is very exaggerated. But I'm doing this so that you can kind of visually see it. I mean, if I had a little sliver of a beam that was like yay wide and trying to show it, like it would just be kind of difficult to see what's going on. So this image, just so everybody's clear, is kind of cartoonishly magnified. Now, what I'm going to do for this deflected portion is I'm going to see if I can determine an expression for ultimately the strain and the stress. Let's start off with the strain. Okay, how do you define strain? Like going back to basic, mechanics. Strain is defined as the change in length divided by the original length. So what about, or the initial length, however you want to say that. So let's talk about the initial length. So here's this beam segment, and what I've got here is the beam that's bent. And if you look at this segment, this solid line that you see here, that solid line right there is the centroid. Okay, and what you might remember from mechanics is that when you have something that's undergoing bending, we assume that there's zero bending stress at the centroid, and that above and below the centroid, it increases, proportionally. And so if there's no stress at the centroid, there's no strain at the centroid, so there's no deformation at the centroid. So I propose that the length of this solid line is the length of the segment before it deformed. And it's probably been a while, but you should remember this formula from geometry. Like if you have a circular segment that subtends some angle theta, that the length of that segment is just the angle times the radius. And so the angle times the radius will tell you how long that segment is. Likewise, we can use the same philosophy to determine what is the length of this segment right here, because that's the one that we're really interested in, because that segment has undergone deformation because it's shorter than what it was before. See, before you bent the beam, that segment was just rho theta long. Now it's rho minus y times theta because it's gotten shorter, right? And so I do a little bit of algebra and I say, okay, I've got an initial length, a final length. If I've got an initial length and a final length, I can determine the strain as, change in length divided by the original length. Do some algebra, cancel some terms out, and I get this term right here as the strain, and then E times the strain. Now I've got a term for stress. Okay. I know there's a lot here on this slide, so I'll take a second and see if this makes sense, if everybody's good with this. Okay. Now, what we do with that term for stress is we compare that to what equilibrium yields. In other words, this is what we're getting, so this term here on this slide is what we're getting. This is what stress is from a deformed structure standpoint. Now, what is the stress from an equilibrium standpoint? And so the way that we do that's pretty easy. We just say, okay, what is the force in each element? And so the force in each element is going to be the stress in that element times the area, right? Sigma equals P over A, so the force is the stress times the area. So the area is that dA term. The stress is, whatever the stress is. I take that force, multiply it by a moment arm, and then if I integrate that, that'll tell me the moment in the section, right? So the moment in the section is just sigma y dA. We have to throw a negative sign in there because that just comes sign convention that we use when we draw our moment diagrams and whatnot, like smiley face positive and what have you. And so what I do is I take this expression for moment right here. I plug in what I had for sigma, and I get this term here. And that integral of y squared dA, that's the moment of inertia. And so I can replace that with that term, that moment of inertia, and I get this. And then the last thing that I do is I take this expression, rewrite it a bit in terms of curvature. Then I go back to that curvature expression that I pulled out of my calculus textbook. And I look at that curvature expression, I'm like, that thing is nuts. That is a crazy expression. Is there anything I can do to simplify it? Well, we're talking about beam deflection. We're talking about small deflections. And so, small deflections mean small slopes. And if I take a slope and I square it, I'm going to get a really, really small term. So anytime you see like a derivative squared, a lot of times in engineering, we can kind of neglect it. So if I take that derivative, that v prime on the bottom of that fraction, set it equal to 0, then the curvature just equals the second derivative, and I get this right here, that the second derivative of deflection is m over EI. This is what I meant by the differential equation that we're going to derive today. And that differential equation is, without a doubt, one of the most important equations in all of mechanics. It is foundational to what we do in a lot of engineering engineering applications. It's incredibly, incredibly important. Okay. Again, I haven't heard much chatter in chat. If you're with me so far, I'll jump right into virtual work. Okay. So let's talk about virtual work. Okay. So we're going to talk about how we can use the method of virtual work to determine displacements and rotations. And then I also want to talk about the units that we use. You know, we do operate in U.S. units in America, and you know, we could argue, you know, there's that debate as to, you know, should we operate in SI or whatnot. But until Home Depot starts stocking tape measures and meters, we're civil engineers, and so we have to operate in U.S. units. And so when you're working in deflections, there's some unit conversions that you kind of have to use to make everything work out. And so we'll derive those, and then we'll jump into an example. Okay. So let's recall that in the method of virtual work that we analyze two structures. We analyze the real structure with all the loads present, and then we analyze a virtual structure, which is a structure with a single unit load at the point of interest. Okay. Now with beams, we can be interested in determining two things. We can either be interested in determining how much that beam displaces or how much it rotates. So what I mean by that is, you know, if I have a beam here, and I'll use my shoulder here for a second. So if I have a beam and the beam displaces, you know, the beam has undergone this displacement, I can be interested in two things, not just like how much it displaces, like what's that actual distance that it's gone up and down. So I'll call that a displacement, but also the rotation. So if I have the beam, you know, here's the beam where it's flat, and here's the beam where it underwent a displacement. Not only did it just move up and down, but it also rotated. Right? It has a slope to it. So if I take like this point right here, this point is at a slope, I might be interested in also determining the slope or the rotation of the beam. Well, if I'm interested in determining the displacement, I apply a unit load. If I'm interested in finding the rotation, I apply a unit moment. Okay. So let me go to that right here. So if we're interested in computing displacement, place a unit load. If we're interested in slope or rotation, place a unit moment. And I'll go ahead and tell you right now that there's a couple terms that I'm going to use interchangeably and that the book may use interchangeably. So if you're talking about beam deformations and you talk about slopes or rotations, they mean the same thing. And displacements or deflections often mean the same thing. So if I ever use those terms interchangeably, that's what I mean. Now, just like with truss deflections, we assume a direction for the displacement or the rotation. And if we get a positive answer, that means our assumption is correct. And so that'll become clear in our example today. Now, because we're dealing with moment diagrams, you know, we're talking about moments. Moments, I don't know if you remember, but think about diagram on the exam. Think about all the homework problems we did for moment diagrams. I don't remember very many moment diagrams that were constant. They were always, you know, going up and down, locked to a little. They were curved. They had, you know, they were always, you know, crazy. Moment was a variable. Moment was a function of x. Okay, so what we're going to have to do is we're going to have to integrate to find, you know, our energy. So, you know, we're going to have that U2 term. If we can determine that U2 term and sum that up, that's going to be our deformation. And so the way that we do that is we use that differential equation. Instead of forces and displacements, we're looking at moments and rotations because that's the differential equation that defines the behavior of the beam. And so that little incremental rotation right here, how do I determine that little incremental rotation? It's just m over EI dx. I'm just, taking that, rearranging it, and solving it for d theta. So if I have that, I can, write out my little incremental energy component right here and sum it up. Sum that up, and boom, there's your displacement. I'm going to leave it on this slide for a little bit because I've gone through a lot of derivations and a lot of math, and I know that can be kind of heavy on a Monday morning. But this method and this slide that you see here is really probably one of the most important slides for this entire week. Okay, so if we're trying to compute the deformation of a beam, we've got a bunch of terms that we need to do. We've got our real moment function, our virtual moment function, which we'll go through an example on how to do this. But just like with trusses, where we had real internal forces and virtual internal forces, we're going to have real moment functions and virtual moment functions. And the real moment functions come from the original loads on the beam, and the virtual moment functions come from a single concentrated force or moment on the beam, depending upon what you're trying to find out. Again, you put it at where you're interested in finding deflections. It has a magnitude of 1, and you put it in the assumed direction of the deflection. And because of our differential equation, it's not EA, it's EI. So the modulus of elasticity and the internal moment of inertia. There's a typo there too, because I have inertial. There's a typo there. Okay. Now, the reason why I have it written sort of like this is because, and this isn't going to affect anything we do today or anything that you do for your homework, but when you look at moment diagrams, sometimes you need multiple equations to define your moment diagram. And because you need multiple equations to define your moment diagram, sometimes you have to do multiple integrals. That won't matter today, but that'll matter on Wednesday and Friday. But we're going to take it slowly into this process. Now, before we jump into examples, we have to look at units. Okay, so let's start off with the differential equation for the deflection of a beam. So this is our foundational equation, that the second derivative of deflection is m over EI. Okay, now if I have the second derivative of m over EI and I integrate that once, okay, now what I'm showing here, I'm not showing that this is the answer, like ml over EI. I don't want you to think that, like, the integral of that is always m over EI. I'm looking at this just from a units perspective. Like, for example, let's go back to Calc 1. If I have, let's say, x squared, and I integrate that, what do I get when I integrate x squared? Somebody tell me the integral of x squared. I want to make sure everybody's awake this morning. What's the integral of x squared? There we go. Somebody's right. X cubed over 3. Exactly right. So the point is, if I have a function like x squared and I integrate it, I get one more x term. Like I get x cubed over 3. So there's another term in there. And so for beams, because we're integrating across the length, there's going to be a length term in your theta expression. And if I integrate it one more time, I'm going to get like L squared. So like the integral of x squared is x cubed over 3. What's the integral of that? Well, there's going to be an x to the 4th term in there. So see how, like, like if you integrate once, you're going to get a length term. Integrate twice, you're going to get another length term. And so my rotation is going to be in, like these are going to be the units. And for deflection, like these are going to be the units. They're going to be in this unit system. Okay. Well, let's see how that stacks up with typically how we express quantities in US units. And what happens is, if we look, let's talk about how we, this is civil engineering. Typically, when we're talking about forces, we've been using kips to express forces. And we've been talking about member lengths, we've been using feet, right? So moments would be in foot kips. Those are the units that we've been using. What about the modulus of elasticity? Modulus of elasticity, typically, we've been saying things like KSI. And a moment of inertia is a very common one, is inches to the 4th. And so if you carry that out, what happens is, like, okay, let's say you're looking at deflections. If you plug all these quantities in, you get something that doesn't really work out. You've got feet cubed over inches squared. And so we got to deal with that to ensure that that quantity is usable. I mean, if I have a beam that's undergoing deflection, how do like what would I want that to be in? If I have a beam that's deflected, I might say it deflected, I don't know, a couple inches. And so what I want is that deflection to come out in inches, but it's not. And so in order to handle that, I gotta do a conversion, a unit conversion. Similarly with the rotations, I'm getting foot squared over inches squared. It's not working out. So I have to ask myself, what do I want my answer to be in? Displacements, probably inches. Slopes and rotations, I could do radians, but honestly, I've always found that degrees is a little more usable. So what I'm doing for displacements is, let's take displacements first. So I got foot cubed over inches squared. So I need to convert each of those feet into inches, so 12 inches per foot, but I have to do it 3 times. So 12 times 12 is 144, times another 12 is 1728. So that's my unit conversion factor for displacements. Don't worry, we'll use that here in a second. As for rotations, we only have to do 2 inch conversions, but then I want to convert that into degrees. That's why I have 180 over pi. Okay, I've been talking a lot. I think the best thing to do is to jump right into an example. I think you're gonna find this is actually a lot easier than it sounds. For some of you that are like, oh my God, Dr. Mike is throwing all sorts of equations and math at us. I promise you, after this example, you're gonna find that this is really straightforward. And I have a homework assignment, which is also pretty straightforward. Trust me, we are gonna ease into this beam deflection stuff. Okay, so we're gonna determine the vertical displacement and rotation at point A on the beam shown by using the method of virtual work. I've given you the E value, I've given you the I value, and we're going to determine how much that beam displaces and rotates. Now, one thing to note is there's a coordinate system on the beam. I'm giving it to you now. Later on, we'll define it ourselves, and there's some ways that you can do that to make your life a little easier. Let's jump right into it. Okay. So let me show you how this works. And today I'm going to kind of walk you through it. As we get a little bit more practice with this, I'll get you all to interact with me a little bit more. Today is probably going to be me kind of holding your hand through it. What we're going to do is we have this beam being subjected to a distributed load. It's 2.5 kips per foot, and the beam is 15 foot long. Okay. First thing that I want to do is I want to determine a real moment function. So real moment function. And we'll call this capital M of X. Okay. Now, in order to determine a real moment function, what I need to do is I need to break out the secret weapon of structural engineering, which is a samurai sword. Okay. So I need to cut a section through the beam. Okay. And now I'm going to cut a section. Where am I going to cut it? I'm going to cut it at some distance X. Okay. All right. Now what I'm going to do is I'm going to cut that section. So again, samurai sword or lightsaber through the beam, and I'm going to cut a section and look to the left. The reason why I'm looking to the left is if I look to the right, I'd have to compute those support reactions. I actually don't need to worry about computing the support reactions if I look to the left because they aren't there. In fact, if I look to the left, all I see is I see the beam and I see the distributed load. That's it. All right. So this dimension here is X. And remember, whenever you cut a section through a beam, there's an unknown, unknown shear, unknown moment. Okay? Unknown shear and unknown moment. I don't really care about the shear, but it's there, and so I might as well go ahead and just throw it out there and mention it. Now, this is 2.5 kips per foot. Now, remember, I can take that distributed load and I can idealize it as a single point load that's 2.5 times x. And then this direction here, let's see if everybody's paying attention. What's that moment arm right there? Let's make sure everybody's paying attention this Monday morning. What's that moment arm? X over 2. There we go. All right. And so if I sum moments at the cut, I've got 2.5x times x over 2, and then m, both contributing moment in the same direction. So what happens is I get 0 equals m plus, what is that, 1.25 x squared, or m of x is minus 1.25 x squared. Now, think about this. So we got a moment function. Let's make sure that we connect this to what we had done before. Okay, that moment function, if I put that in Excel, or if you don't want to use Excel, if I just graph that, what that's going to show me is the bending moment diagram. Okay, and what I get is a function that's negative. Well, that should make sense. If I look at the beam, if I look at those loads, that's going to make the beam go frowny face. All of that beam is experiencing negative moment. Okay, so that should make sense. All right. Now watch this. Now what we're going to do is a virtual moment function for the displacement at A. Oh, goodness. And so what do I mean by a virtual moment function for the displacement at A? Well, I take my structure. Here's my structure. This dimension here is 15 feet. Or wait, is it 15 feet or is it 20 feet? Yeah, 15 feet. I'm getting it mixed up with the homework problem because the homework problem is 20 feet. And this right here, this is point A. This is point B. All right. What I do is I say, okay, I need to ask myself, this is point A, and I want to determine the displacement, or the vertical displacement. I mean vertical displacement. And I need to ask myself, if I go back to the original structure, do I think point A is going to deflect upwards, or do I think it's going to deflect downwards? And I don't know about you, but I kind of think it's going to deflect downwards. So I'm going to place a single unit load downwards at point A in my assumed direction. And then I'm going to do the same thing. I'm going to cut a section, you know, where this dimension's x. I'm going to cut a section. I'm going to look to the left. And when I cut a section and look to the left, what do I see? I've got my shear. Actually, let me do this. I've got my shear and my moment, but I'm going to label that here in a second. I've got 1.0. This dimension's x. And then to label these are virtual moment functions. I'm going to use little letters. So maybe, you know, a lowercase shear and a lowercase m. Again, I don't really care about the shear, but I'm putting it there just to be consistent. And then I do the same thing. I sum moments at the cut. And what do I have? I've got my little m, And then instead of that 1.25 or that 2.5x times over 2, all I have is the unit load of 1 multiplied by the moment arm of x. So 1.0 times x. So in other words, 0 equals m plus x, or m of x is minus x. All right, is everybody with me so far? Okay, awesome. So to do the method of virtual work, it's really simple. So we've got a little m of minus x and a big M of minus 1.25 x squared. We have an E value of 20,000, and we have an I value of 1,500. So what we do then is we say that the deflection is the integral of little m over EI. And so let's evaluate that. Okay, so first off, we're going to have the integral. We're going to have minus x minus 1.25 x squared over EI. E is 20,000. This is 1,500 dx. Now, a couple things that we have to fill in. Okay, first off, we need to put in the limits. Okay, if you remember, this beam is 15 foot long. So remember, we're trying to sum up the energy around the entire beam. So this is going to be from x equals 0 to x equals 15. Okay, and then the last thing that we need to do is we need to include that unit conversion factor. And for deflections, that unit conversion factor is 1728. All right. Now, what I'm going to do from here is, at this point, this is a calculus problem. Okay, this is just straight up Calc 1. And so the way that I'll do this is I'll say deflection equals 1728 times 1.25 over 20,000 times 1,500 times the integral from 0 to 15 of x cubed dx. Now, this part right here, you should be able to do that. If you want to use your calculator, like your Casio will actually do this. If you do this in your Casio or in your calculator, what you will get is 12656.25. That's what you get if you do that in your calculator. And so if you take all this, the 1728 times 1.25 times that divided by these, what you'll get is the deflection equals, or not, I'll do it with you. You get 0.911. Okay, and what that tells you is it came out positive, so our assumed direction was correct, and this conversion factor of 1728 converted our answer to inches. It's that simple. We only have about a minute or so, so I want to show you something real quick, but before I do, does anybody have any questions? Does that make sense? Good deal. All right, I want to show you something real quick. For rotation at A, here's what you're going to do. For rotation at A, you're going to have a beam that instead of having a point load, it instead is going to have a single concentrated moment at A. And if you cut a section at X, you're going to have, something like this. What you're going to find is m of x, instead of being like minus x, it's just going to be minus 1. And to determine the rotation at A, what you're going to do is you're going to integrate m of x over EI, which is going to be the integral. It's going to be from 0 to 15. It's going to be minus 1 minus 1.25 x squared over 20,000 times 1,500. Although instead of your conversion factor being 1728, it's going to be 144 times 180 over pi. And so when you chug that out here, I'll do it for you real quick. You should get the theta at A is 0.387 when you do all of that. And so our unit conversion factor tells us that that's in degrees, and then our fact that it comes out positive says it's in the direction that we assumed. Now, here's the thing. We're going to have a lot of practice on this. So if today went pretty quickly, first off, the homework assignment that I gave you is pretty easy. It's you don't even have to do rotation. You just have to do deflection. And it's one problem. It's a really easy problem. Trust me, we're going to ease into doing deflections, and we're going to spend a lot of time on it. By the time we're done with it, you're going to be very, very comfortable with it. Any quick questions before we call it? All right. Okay. Well, you got a homework assignment due Wednesday. I'm going to go ahead and stop the recording. You all have a wonderful day. Let me know if you have any questions. I will see you all on Wednesday.